Hello everyone, this lecture video is all about cerebrospinal pressure, and let's start. So here, the skull here, and then the spinal column, it contains the cerebrospinal fluid or CSF, the one that is color blue, the cerebrospinal fluid here, the blue ones, those are the fluid. So this as well, an enlarged portion of that. The blue one is the CSF, and then here we also have here the blue ones, CSF. So what is the purpose of that? Okay, another CSF. And then, so the cerebrospinal fluid supports the weight of the brain with buoyant force. So the buoyant force here, it means float. It allows the brain to float on that liquid. So when it allows that to float, this is, let's say this is your brain and this is the fluid, that us use the color blue one. It protects the brain itself from the physical blows outside or externally. So what's the purpose of CSF? It acts as a protective cushion for the brain, and it also supplies nutrition filtered from the blood. So the color of the CSF is colorless. But there are instances when there is a problem with your CSF that it became yellowish or an orange or reddish, but the normal color is colorless. The CSF is generated in the skull. It circulates around the brain through the ventricles. So we have here the ventricles. This is the pathway of the cerebrospinal fluid. And down to the central canal of the spinal cord. So your spinal column here, it has a central canal in which the CSF will flow. It's like a canal, a pathway for the fluid. So the normal process for CSF, it is absorbed in the spinal column as fast as it is generated in the skull. However, there are instances that the narrow ventricle called the cerebral aqueduct. We have here the ventricle, right? So there are narrow ventricles and we call it as cerebral aqueduct. So this narrow ventricle, there are times that it may be blocked. Maybe it can be blocked because of the nutrients, solid portions of the nutrients, or just if you have a high blood pressure, for example. So when it happens, when there is a blockage in the cerebral aqueduct, there will be an increased pressure that will build up inside the skull. So when that happens, when there is a build up, there will be a hydrocephalus that is very common in infant. There will be an occurrence with that. So hydrocephalus, we call it as waterheads. And then hydrocephalus causes the infants to have an enlarged head, and then that will cause, the enlarged head will cause mental retardation or even death. But when this case has been detected earlier or in an early phase, the pressure and its effects can be minimized surgically. So how do we measure the CSF pressure? We are using the water manometer. But unfortunately, this method does not detect hydrocephalus because the blockage in the aqueduct, in the cerebral aqueduct, prevents the excess pressure in the brain from being transmitted to the spinal column. It is not convenient to measure pressure in the brain directly because of its bony structure. So other methods of detecting hydrocephalus are generally used. Example, shining light through the soft skull, and then ultrasonic scans, and then the x-rays. Then let us discuss the spinal taps or the lumbar puncture. This is the spinal taps, as we call it. It will puncture on the lumbar part here. Okay. It will collect a CSF on this part. Okay, just like this one. It is being, the CSF or the fluid is being drawn between the two vertebrae here, and then the patient position can be either sitting position or lying position. So why do the doctors conduct spinal taps or lumbar puncture? First, to administer anesthetics immediately directly on the brain, and then to introduce dye for contrast to on an x-ray, to withdraw CSF for density measurements. So that is the purpose of withdrawing the CSF here, to measure its density. And then there are side effects of spinal taps. One is severe headache. So the treatment for this is that the patients are instructed to lie motionless on their backs for several hours following spinal taps to avoid the CSF leak or the leakage of the CSF in the entry point of the needle. The skull and spinal column contain about only 125 cubic centimeter of CSF. So even a small loss is very significant. It is very important in the buoyant force because if the brain has a low CSF, it will be deprived of buoyant force, it will be deprived of the oxygen as well, and there will be a less protection from physical blows, and you will be experiencing severe headache. So in that case, the patient is asked to just lie down because the replenishment of CSF occurs every 4 to 5 days, and lying down flat distributes the CSF evenly throughout the spinal column and up to the brain. Now let us perform some sample problems. I have here a figure, this figure here. So this sketch is a water manometer used to measure the CSF pressure here. If pressure in the CSF is measured as shown in the previous figure, this one, using a spinal tap with the patient sitting erect then the pressure due to the weight of the CSF in the spinal column increases the pressure. The first question is, what pressure is measured in centimeter of water if the pressure around the brain is 11 millimeter mercury? This one. Pressure of the brain is 11 millimeter mercury. And the top is at the point, which is 70 cm lower than the brain. This is the top here. That is 70 centimeter. Then the second question, what pressure in centimeter of water is measured if the patient lies down? The density of the CSF is 1.05 grams per cubic centimeter. Let us proceed for solution A. Remember that the 1 cubic centimeter of water is equivalent to 98.0638 Pascal. The Pascal is the pressure, and this is also a pressure unit in a smaller scale. So for solution A, since the bottom of the manometer is at the same vertical height as the needle, the pressure measured in the manometer is this formula. We will be using this formula. So the formula is this one. Pressure is equivalent to the height and the density of the CSF multiplied to the acceleration due to the gravity plus the pressure of the brain. Let us proceed. First, let us determine the given values for P is equals HPG. Let us have this one first. This one, HPG. So the H is equivalent to 70 cm, which is the height. This one, where is that? This is 70 cm. Since you are being asked as sitting erect. And then you have to convert that into meters because that is the standard SI unit here. So 0.7 m. And then the density of the CSF is given as well based on this problem, which is 1.05 grams per cubic centimeter. But you have to express that in kilogram per cubic meter, this one. So that is 1.05 grams per cubic centimeter. And this is the value that we will be using. Convert that into kilogram per cubic meter, this one. So you just have to add three zeros on this case. That is why that is times 10 raised to 3, and then you just have to change this into kilogram, the cm3 into meter cube, since you converted, you added 3 zeros. And then the acceleration due to gravity, the g here on this part, the g here is equivalent to 9.8 meters per second squared. This is constant. Again, this is constant. Next is the value of the pressure of the brain. So the pressure of the brain based on the figure is 11 millimeter mercury, this one. And then the next that we need to do is break that down. So since you express this in meter, you have to express the 11 millimeter into meter as well. So 11 millimeter is equivalent to 0.011 meter. This is the value that we will be using. The mercury, okay, the density of the mercury is equivalent to 13.6 times 10 raised to 3 kilograms per cubic meter. And then the acceleration due to gravity is 9.8 meters per second squared. So these are the values that we will be using. And the formula for that is this one to solve that. So substitution, you just have to substitute. So P equals HPG plus B. The value of the H is 0.7 m from here. This one. Multiply to 1.05 times 10 raised to 3 kilograms per cubic meter, which is the density of the CSF. And then given here, this one. And then next, this one is 9.8 meters per second squared, given here, this one. And then next, plus the pressure of the brain, in which you will be using these formulas. This one. That will be 0.011 meter multiplied to the density of the mercury, which is 13.6 times 10 raised to 3 kilogram per cubic meter. And then the acceleration due to gravity is 9.8 meters per second squared. So if you will expound this one, that is the elongation of the pressure of the brain. The pressure of the brain is also equivalent to HPG, given that the density of the P is the mercury instead of the given CSF here. So perform the operation, you will have 8,669.8 here, or just 8.7 times 10 raised to 3 newtons per meter squared. Why? Why this unit? So let me expound the unit. So the first thing that we need to do, we have here a meter. Since it does not have a denominator, meaning to say this is one is a numerator. So the numerator meter is at the top, and there is an imaginable 1 here. Then multiply to the kilogram per cubic meter, this one. Let me use another color here. Okay, this one. Okay, ayan. And then we also have the meters per second squared, the unit here, this one. And then plus the meter here, which is in the numerator. And then the kilogram per cubic meter here. Where is that? This one. And then the meters per second squared. That one. So we only need to do some cancellations here. Since it's opposing, cancel the meter, you will have a kilogram meter squared instead of 3. Law of sign. In division, you will subtract the exponent because they are in opposing side. So you will have now here kilogram per meter squared instead of cube. And then you have here a meter, so you will be left out with kilogram per meter second squared. Okay, minus 1. Same here, since they are also the same, you will have kilogram per meter second squared. And in the rule, since they have the same unit, you will just copy that. And kilogram per meter per second squared is equivalent to Pascal, and Pascal is equivalent to Newton per meter squared, which is also a derived unit. So that is how we get the unit here. The next thing that we need to do, since you are being asked to express your answer in the centimeters of water, this is not in centimeters of water, we have to express that in centimeters of water. The next thing we need to do is use this formula to convert that into centimeters of water. You have here the formula, and we want the value of the HW for the centimeter of water. So to do that, we have to divide both sides, the P equals HW PWG, into PWG. Dividing both sides by PWG, we will cancel this out, and you will be left out with the HW equals to the P over PWG. Okay, so the value of our P is based on the answer here, which is 8.7 times 10 raised to 3 newtons per meter squared, this one. And the value of the PW, or the density of water, in kilogram per cubic meter is 10 raised to 3 kilogram per cubic meter. And the G, or the acceleration due to gravity, which is constant. This is constant, okay, 9.8 meters per second squared. Next, the thing that we need to do, substitution, since this is the formula, the value of the P is 8.7 times 10 raised to 3 newtons per meter squared. And then, next, the PW, or density of water, is this one from here. 10 raised to 3 kilograms per cubic meter multiplied to the acceleration due to gravity. And then, let us cancel some units. If you will expound the Newton unit here, the Newton is a derived unit, and Newton is equivalent to kilogram meter per second squared. This is this one here. Okay, over the meter squared. So again, before you get confused, this one here is Newton. Okay, if you will expand the Newton unit, that is equivalent to kilogram per meter second squared, and then over the meter squared. Then we can cancel some units na. Let us cancel some units. Cancel the kilogram here. Cancel the kilogram. Cancel the m cubed here, and the m, you will be left out with m squared, so you will be able to cancel this one. Cancel the second d here. You will be left out with the meter unit. Okay, so here, if you will perform the operation 8.7 times 10 raised to 3 divided by 10 raised to 3 multiplied to 9.8, you will have 0.8877 meter, because the left unit is meter. Then you have to convert the meter into centimeter. Converting meter to centimeter, you will have 88.7 centimeter. That is 88.8 centimeter of water. This is the answer for A, 88.8 centimeter of water. And the next solution for letter B, the problem again, we have here, what pressure in centimeter of water is measured if the patient lies down? The density of the CSF is 1.05 grams per cubic centimeter. So let us proceed on solution B. So if the patient lies down, based on the problem that is being asked, then there is no excess pressure due to gravity, and the pressure measured will be equivalent to the 11 millimeter mercury, the pressure of the brain. So therefore, here, the pressure is equivalent to the pressure of the brain, because there is no excess pressure from the gravity, because the person is lying down. So the P again is HW. If you will expound this P, that is HPG. So HW, PWG, and then the pressure of the brain is HPG as well from the previous example. So wherein the H is the height of the PB, the P is the density of the mercury, and then G is the acceleration due to gravity. So we don't need the G anymore because the person is lying down. So we have to cancel the G unit here, cancel that. So what we need to find is the HW here. Okay, so we have to manipulate the formula. I'm teaching you how to manipulate the formula. So to do that, you just have to divide both sides in PWs. Okay, show you that you can have the HW. So dividing both sides with PW, you will be able to cancel out the unit here. And then, therefore, the formula that we will be using here is the centimeter of water is equivalent to the height based on the pressure of the mercury, and then the density of the mercury over the density of the water. So let us get the given values. The HAG is equivalent to 11 millimeter. You don't need to express that in meter because, again, we don't have the other units. We don't have to cancel much units. Or the density of the mercury is 13.6 times 10 raised to 3 kilogram per cubic meter. And then the density of water is 1.0 times 10 raised to 3 kilogram per cubic meter, or just 10 raised to 3. It's up to you. They are the same. This is constant as seen on the previous example. And then substitution, here is the formula, and you just have to substitute. The HW is equals to the HHG, which is 11 millimeter, and then the PHG is equivalent to the 13.6 times 10 raised to 3 kilogram per cubic meter. Then the PW, or density of water, that is constant, 10 raised to 3 or just 1.0 times 10 raised to 3 kilogram per cubic meter. And then we can cancel out the units here. We can cancel that, cancel. You will be left out with the millimeter unit, and perform 11 times 13.6 times 10 raised to 3 divided by 1.0 times 10 raised to 3 millimeter. So that is 149.6, and you have to convert the millimeter into centimeter. Converting that, you will have 14.96 centimeter of water. This is the answer for letter B. So that is all for cerebrospinal pressure.